And we're back. No, welcome back.
Welcome back. Hello. About hello, friends. Welcome to part something or another of everything you didn't want to know about propellers. And we're hoping I wouldn't tell you. All right. So we left off talking about mostly, we did nomenclature, props. We talked about how Orville Wright basically said this thing is crazy. We're not even sure where to begin because the angle depends upon the rotational speed, which depends upon the forward movement of the aircraft, and that's sort of where we're headed with this. So one of the things we talked about last was the blade element theory. It's not really a theory. I don't call it a theory. I mean, it's a fact. And if you look at it, if you take a 1 inch, if you take a cross-sectional area of a blade every inch, I don't know, every 6 inches, according to this, every 6 inches, you can see how different each one of those is going to look on the exact same propeller. And we could see if we looked at this, I don't think I can do it, do it right here. If you look at this angle, I think blades like that. And then it's like this, then this, and this. It's starting to flatten out. So the difference between right here and right there is pretty significant.
Yep.
Well, if it's the same propeller attached to the same engine, rotating at the same
Speed.
RPM, I'll be careful how I say that because it's not the same speed. Why does it look like that? Well, the reason why it looks like that, probably just jumped ahead of myself. I did. So I guess we have to, the reason why it looks like that is because what I'm going to tell you about in a minute. Let me think. A couple things we need to know about this one. I think we're back to, got ahead of myself. We'll circle back to that. All right. There we go. We're at theory. If I would have looked at that. What is the theory of a prop?
Spin increase thrust.
Well, I have a lot written, so I'm going to kind of try and reduce some of this. So you can write some things, but definitely it's a rotating wing, right? But turns around on this plane. So it's a rotating wing. So we talked about the blade element theory. And what is the blade element theory? Each section is made up of small airfoils. And they change as we go up and down. And we take all these little made 1 inch airfoils and we glued them all together for optimal use on we end up with a propeller. So, all right. So each element is made, or each section is designed. To operate at its best angle of attack. So we have all these different little blades put together, sections that are going to create the blade. This gradual change, we see if that's 2, then this would be A, and this would be, I could do this. 1, 2, 3, there we go, all right. This gradual change is called pitch distribution. Pitch distribution. So if we look back at that picture and think about it, well, each blade has a different cross section, a different angle, a different chord. So it's very, very different from the next. It's not just the same look. Not just the same look, angle different. They look significantly different, I would say. All right. Maybe, did you ever notice that? All right, or not.
And it's basically the farther out you are, has a different angle or speed that has to
The whole thing?
be.
Further out, well, further in too. Works both ways. Further out you go, it's a different speed. Further in you go, different speed. All right, so blade is designed to create thrust. A, B. Let me see. what is the official definition? Prop converts horsepower, shaft horsepower, to what? Thrust. Thrust. So what is thrust? Well, according to Q&A, whenever I say according to Q&A, it usually means I don't buy into it too much. According to Q&A, thrust is produced by a rotating propeller in the same way lift is produced by a wing. That makes sense. Area, so thrust is produced in the same way a wing produces lift. And how does a wing produce a lift? I have to go get Phil? Hey, you guys are talking now. Hell no. All right. So what do we have then? Have a wing. What's on top of a wing?
Low pressure.
Low pressure. So where would that be on a propeller? Okay. So an area of what? Decreased pressure in front. And so if you have a low pressure in front of the propeller, it will do what to the prop?
Pull it forward.
Pull the prop into low pressure. I guess I put according to Q&A because I kind of have a hard time swallowing that one, moving my plane through the air. I mean, obviously it does do that, but so the Q&A says that. However, I will add, let me see, some books or many books. I don't know, some or many. Well, some or many, I don't really know. Some or many books. Add, what do you suppose it's going to add?
High pressure, under.
What are the two ways, let's talk about it. What are the two ways that wings actually produce lift?
Yeah, velocity.
What do you have on top? What's that? Newton. Newton's third law. Every action has a...
Reaction.
All right, so what's the action?
Drag.
Not drag.
That's
What's that?
Beating against the air.
No, there's got to be action or reaction. I don't.
Thrust, there's drag.
yeah, throw some drag.
That's not lift.
Oh,
yeah.
lift.
Oh.
Low pressure area on the top, there's going to be a high pressure area on the bottom.
No, it's
No,
what's the other one?
I've got 3 CFIs in here. I should be able to get this answer. What's that?
So you got thrust, right, going backwards, and that's going to push you forward.
Yeah, but what's the lift?
The lift goes over the wing and it goes down.
Hangs down. Over the wing? Under the wing.
The top part of it goes over the top, and part goes on the bottom, but the
Yeah.
part on the top is curved and it goes towards the ground.
This is a restriction which then increases velocity, lowers pressure.
What's that?
Well, because it has to go over the restriction. Lowers your pressure above.
You got that?
there we go.
So there is a really, not was, there still is. I don't think anybody's burned it. Called Stick and Rudder by Wolfgang something or Longenstein or something like that. So I remember I had a customer many years ago gave me this book and I took it home and I was reading it and I came to work talking to a CFI, former Navy pilot, and I said, this book is really cool, you know. In all of my books at AMP school, they never talked about Newton's third law. They always talked about Bernoulli's principles being the way wings worked, right? Air went over the top, had a longer way to go, have increased velocity. Increased velocity equals
Low pressure.
decreased pressure, sucks the wing up. There you go. End of story. Well, honestly, when I went to AMP school so long ago, that was it. Done. End of the lecture. Moving on. And this book, Stick and Rudder, the guy talked a lot about Newton's third law, where imagine the wing being canted a little bit, the air is going to push down, or if you like, I like yours where it goes over the top, because when you really look out the wing, when you're flying, it's pretty freaking level. But anyway, that is going to cause air to go down. Well, that air mass going down is going to cause that's the action, so the equal reaction is the wing being pushed up. So you don't have to have an airfoil shape to have a wing.
Paper airplanes fly.
What's that?
Paper airplanes fly.
Paper airplanes fly. That's a good point. Now we're getting into some weird stuff, but it's called a Reynolds number. Has anybody heard?
That sounds.
Yeah, you went to San Jose State, so this is bringing back some horrible memories. But yeah, it's all based upon Reynolds numbers, based upon a flat plate of steel, I believe it is. It's a flat plate, and that's it, and how that flat plate will fly in a wind tunnel sets up the basis for how wings work. Blah blah blah. Anyway, getting out of that. So many books add Newton's third law. Or suggestion. I mean, you know, which is for every action, there is an equal and opposite reaction.
That's kind of like Richard Peak and Lena Peak, though. There's a lot of arguments about that.
Yeah, I bet there are. Oh, yeah, to finish my story, when I told the story about this, but they're like, you need to burn that book. You need to throw it away. There's no Newton's. That is, okay, I wouldn't even, there's nothing in this thing that has any redeeming value. Don't read it. And now today, it's almost like a required reading. I mean, this guy was just so far ahead of his time that everybody was, burn him at the stake kind of a thing. Not like, oh, you got to read this book. Okay. And the two are directed across the same line as it goes. So what is action one of the prop? Action one. What do you suppose that is?
Pushes air back.
Pushes air back. Okay, so we got acceleration of a mass of air by the blade. So acceleration of mass of air, I'll put that by the prop toward rear of airplane. So action two then. So the blade moved a mass of air backwards, therefore, okay, the plane. Let me see, the plane is pulled forward. Well, I had some more notes in here that I just kind of skipped over. I said assume 200 pounds of air. How much does 200 pounds of air weigh? It's going to be an easy test, man. Okay. Well, then the plane is pulled forward with 200 pounds of force. That is an example. Do not assume that all planes have 200 pounds of force. D B thrust. Well, I cut out some stuff. E right here. I don't know how the other ones. We'll just go with it. All right, blade angle. Or if I misspell it accidentally, it'd be a blade angel. So you may have a few blade angels happening in this lecture. I don't know. All right, what is the blade angle? The angle. Yep, going to use chord between the chord. Angle between. Let's try and spell it. I don't know what that said. Between the chord angle between the chord, which is often the face. Why would it be the face of the blade?
Flat.
Because it's flat. And it makes a really nice flat surface to do it. So often the face of the blade of a particular section particular blade section, and the plane of rotation. All right, so blade angle. This is going to be an important one. We talk a lot about it. Angle between the chord line and the plane of rotation. There you go. Let's see. So, let me see. I can write this better than I wrote it here. Optimum. Optimum thrust. Say each blade, each element must be at the proper angle of attack. AOA. What's angle of attack? Chord line to the relative wind. So if I have a wing and I'm going like this, what's the angle of attack?
0.
Well, do that, right?
0 to 2.
Well, what if I don't have a little plane? What if? Look, a little plane. So if the relative wind is right here, we're coming at that, angle of attack would be
0.
What if I'm doing this?
90 degrees. Oh no, it's still 0. Still 0.
Still 0. If I've got this pointed at the direction of flight, what's my angle of attack?
0.
0. Now what's the angle of attack?
Okay, now it's close to 90.
Now it's like 45 degrees, right? Because it's hitting right here.
45 degrees.
Right? Is that going to work that way? For a little while. If you have enough horsepower. Then what's it going to do?
Stall.
And then it's going to fly again. All right, so the blade is the same thing. Blade's going to go through the air. It's angle of attack. Angle of attack like that, if I'm standing still. What would the angle of attack be on a blade that's...
Oh, 0. Yeah.
If I got it like this, I'm going like that, it's 0, right?
Yeah.
But if I start walking forward, it's not, is it? Something's going to hit this way.
Mm-hmm.
So it's going to change. Look at that. Let's see. There's no blade on. Okay. All right, so that brings me to this one. So while rotating, I should say rotating in flight because it's going to change. Each section, that's blade section, each section has a motion that is both forward and rotary. Means it turns in a circle and it goes forward. Talk about pitch. I'm going to hate myself this later. I'm like trying to consolidate and keep things. Okay, so let's talk about pitch then. So actually it's a good time to talk about that. We just talked about blade angle, right? Blade angle is what? Between the chord line and the plane of rotation. All right, so then there's something that is not blade angle. It is called pitch. A, B, C, D, E, F, G, H, we'll call the pitch. Pitch. So pitch is, let me see. Hey, do pitch? Oh, yeah. Pitch. pitch is the distance the aircraft will move forward in 1 revolution. That's kind of the base term right there. So actual definition, we would have geometric pitch. That is the theoretical distance an aircraft, let's see, I'll stick with my words, an element, no, I want to change that. I'm going to say the prop. The prop will move forward in 1 revolution based on the blade angle at 75% station. How's that going? Let me see. Will that work? Yeah, I can go with that. All right, so a couple things to kind of unpack in that one. So first of all, it is theoretical, so it means it's not real. Second thing is the 75% station. So what is 75% station? Well, let me see. If I had, let me see. I won't make it too difficult. If I had a blade, I have an example. So if I had a blade angle that has 20 degrees at station 30. So remember that would be, well, I don't have the actual prop, but it's the prop divided by 2. So if I had a, oh, that's the worst prop I've ever dreamed. All right. If I had a 72-inch prop, now I want to know what the 75% station is. First thing I do is I got a 75% station is going to be from here to 75%. Well, so I take 72 and divide by 2, which will be 36. So we got to look at that. That's 36. And what's 75% of 36? 27. Equals what? 27. So what size prop do you think I have here at station 30 is 75%? Just do the math backwards.
78.
Oh, I actually gave an example here. Well, I can just follow my example. I have an 80-inch prop. 80-inch prop. Let's see. So, what is my 75% station? And this will be on the test. So it's 80 divided by 2. So you got half the prop equals 40 at the 75% station. So that's point times 0.75. 30. Well, there we go. That's how I got the 30. Okay, so we got 30. 30 what? 30 inches from the hub. So 30 inches. All right, so we're talking about right there. So we take a look at that and we say, wow, what is the blade angle? And of course, we're going to assume that the prop is flat, the hub, so that it's not like oblong. So prop goes around, we measure that, and it's 20 degrees. Follow me so far? Looking over there, everybody's got it, okay. So we're trying to figure this out. So we got 30, so our blade angle, why am I using 30?
Because it's 75% station.
And why am I using the 75% station? It's because that's what they told me to use. That's the standard. So they, whoever they is,
Powers that be.
says before FAA, it'd be back in the CAR days, Civil Air Regulations, said you will measure this said propeller at the 75% station, and you will get that angle, and you will do some math with that angle. You will say something like and there's a couple different formulas. I think in the lab I use one, and here I've got another. It will say the geometric pitch equals 2 times pi times times the radius times the tangent of blade angle. There's another formula. What was my other formula? Oh, maybe that's just it. So what do we get? 2 times pi times what's my radius? Well, let's think about the radius. What is the radius? So there's a circle. Is this the radius?
Yes.
And what's my radius?
75%.
75. How many inches was that? 30. All right, we'll go back to this. 30 inches. That's what it was. 80-inch prop. 80 divided by 2 is 40 times 75 equals 30. 30 becomes the radius we're discussing. So 2 times pi times the radius we're discussing times tangent times tan. 2 times pi times tan of 30? 20. Yeah, 20 degrees. Sorry. Tan of 20. Oops, I forgot the radius. Times the radius. Let me do that again. 2 times pi times the radius times the tangent of the angle. I'll just put a little angle sign right there. So that's 2 times pi. What's my radius?
30.
30 times,
Tangent.
is it 20 tan, I think, on your calculator? 20 tan equals, oh, this 20 right here, that's the angle. Where did I get 20?
Gave it to you.
From the, I gave it to you. It was in the thing. It said, hey, you have 20 degrees at station 30.
Yeah.
So there's the 20. There's the 30. Plug it in. What do you get?
421.
What's that?
421.69.
421? No.
68.6.
It should be something like 6.283 times 30 times, and the tangent is like 0.364. So all of that should equal, yeah?
Can you scroll up to where you got 20 again?
It's the angle.
Maybe work that out about that.
It's the blade angle. I didn't bring my calculator in. So what? 68.6 is the correct answer. 68.6. Everybody get 68.6? You're like, no, I'm not even trying because it's not that important.
So on the test, what's going to be the given? It's just going to be the.
Do it one more time. You have a prop. That is 80 inches. And at the 75% station, it is 20 degrees. Go. So, first thing I want to know is what's the 75% station?
30.
I have a prop. What is the 75% station? Right about there and right about there. Well, it is 80 divided by 2 equals 40. So what does that mean? It means from the hub out to here is how many inches? 40. And so that means from the hub to the 75% station is 30. So that's 30 because I did times 0.75 equals 30. What is the angle right there?
20.
Is?
20.
How do you know it's 20?
Because
Because I said so. Then you just got to plug it in. We know that the 75% station equals 30. The angle equals 20. Plug it in. Geometric pitch equals 2 pi times radius times the angle, tangent of the angle, which is 2 pi times radius is 30 times
20.
20 tangent equals
Tangent 20. 68.6.
68.6. Got it?
Mm-hmm.
Yeah. We haven't got there yet. Feet, yeah. Sorry, inches. We're doing inches. Everything was in inches because the radius was in
Inches.
inches. So the answer is going to be inches. If I did this in feet, then this would be feet. So what does that mean? Geometric pitch is 68.6 what? Inches. What happened in 68.6 inches?
One revolution.
Theoretically, every time that prop goes around, the airplane should move forward. How much?
68.6 inches.
There you go.
That's cool.
Why would you ever want to know that?
So you do some cool math.
I have used this in real life.
As a pilot or a mechanic?
Mechanic. Oh yeah. Somebody says, hey, I would, they don't not happy with the performance of their propeller. They want the airplane to go faster. They want to go slower. How many, measure out how many degrees the prop is. Look at how many degrees they can go to. What's this going to do? How much is this going to increase? How much is it going to decrease? You can answer all these questions once you know this simple math. It's either that you can go, I don't know, and call it prop shop. Yes.
This is all theoretical, right?
Yeah, but you start with theoretical. Then you get actual. So it's a theoretical distance. So in theory, this particular airplane is going to move forward 68.6 inches every time it goes around. Well, wouldn't that be wonderful?
Yeah.
It doesn't work that way. That's the geometric pitch. But now we have the effective pitch, which is
How far it actually goes.
how far it actually goes. It's the actual. So if you made a propeller that was maybe just out of some plywood, didn't have a nice leading edge, didn't have a flat, it had flat back because it was, the face because you used plywood. You didn't curve the front.
Is it 5-ply or 7-ply?
Huh?
5-ply or 7-ply?
Oh, it was the 5-ply. It's OXB too. It's not even a good stuff. It's coming apart.
One revolution is.
It's wet particle board.
Oh.
Right? So not everything's created equal.
You definitely better clear
So you got the budget prop. So you get a very low effective pitch. And so that is geometric pitch minus effective pitch equals slip. And those two things are not equal. So effective pitch is about, let me see, well, it can go from 0% to about 85% on a fixed pitch prop. Who would ever buy one that's 0?
The cheap person?
Every prop out there has a 0. Starts out that way. Your feet are on the brakes, which your effective 0. If your feet are on the brakes, it's 0. No matter how hard you push the throttle forward. All right, so pitch is the distance that it will move forward. We have the geometric and the effective. All right. So now you have to keep this in mind. So pitch is used synonymously with blade angle. And blade angle is used synonymously with pitch. That's not technically accurate, but if you're going to talk the lingo in this business, you better get used to it because that's just the way it is. So when I'm controlling my prop, I will use the term high pitch or low pitch. I don't use the term high blade angle and low blade angle very often. It's easier to say pitch. But what I really mean is blade angle. So I will tend to do that as we're talking. If you need clarifications, go, do you actually mean pitch? Or it almost never matters unless you're talking about something very specific, which we will. So low pitch, which really should mean low blade angle, prop control forward, high RPM. We got to get used to that now. What color is that knob?
Red. It's blue.
It's a primary.
Good job trying to trick him.
Very comfortable.
Go ahead and pull that.
Let's see. If you've never accidentally pulled the wrong knob, you're not really a pilot. The trick is how you recover from it. Go to cycle your prop and you grab the mixture and you shut off the engine with passengers in the plane.
I'm just testing something that's weird.
Yep, that's exactly. You pull out your iPad checklist. You go, mixtures check.
I did that coming out of Flagstaff. Started to stumble. I was like, oh, I knew exactly what I did.
Yeah, we usually catch it in time to do that.
Of course, I was with the pilot, so I was like, did it.
Oh yeah, when you're with
Oh,
other,
really?
yeah, that's the worst, right? When you're with another pilot who's higher time than you, and they're like,
Really?
you know, how about I be pilot in command? You swap places. All right, so low pitch in a constant speed prop is going to be the prop control, the blue knob, forward, and that is high RPM. Remember, everything forward is high RPM. It's not high pitch. It's low RPM, high RPM. Low pitch, high RPM is forward.
RPM low pitch.
Huh?
You almost said it backwards.
Almost, not quite. And then if I pull it back, it is high pitch, low RPM. So you're gonna have to make up your mind how you want to think about it. Maybe the blue knob for you is RPM, high, low.
I like that.
All right, now then that's fine because that's the intent. Why it's forward is high RPM, back is low RPM. But you have to also remember that when I push it forward, it's going to flatten the blade out, so I get the high RPM. When I pull it back, it's going to increase my angle. And I'll try not to go too much into keep going back and forth between constant speed and not constant speed. If I have a fixed pitch propeller, which one do you have?
Oh.
Right in the middle. You have the whole thing, one blade. So they try and fit those right in the middle somewhere. So that's somewhere between takeoff and cruise. All right, let me see. There we go. Another slide, same thing. Distance moved in one rotation is low pitch, small blade angle. Is that prop forward or prop back?
It's forward, control forward.
Low pitch. Low pitch is
Forward.
forward, high RPM. Pull it back, you get low RPM, high pitch. And what do they call this? Pitch. What is it really? Right there I have a textbook. They can't even keep it straight. There we go. That wasn't good enough. I got 3 slides for the same thing. Now everybody's going to get this one right. So geometric pitch is the theoretical, and the effective is the actual, and the difference is slip. All right. That was good to put that there. All right, got the blade angle, right? This is a 4-blade prop. I'm used to seeing it, but for many years I would look at it and go, what the hell? It's a 4-blade prop. So they got 2 going up, 2 going out. And they're just showing the one coming out. They're saying that, hey, that blade angle is the plane of rotation and the chord line. That is called what? Nope.
No, that's blade angle.
Blade angle. Angle of attack doesn't come in until we add air. We're not talking about air. We're just talking about that. So blade angle is the
Plane of rotation.
plane of rotation chord line. Pitch is how far it's really moving forward. All right. As long as we got that, now we can just switch them all up. We could just call pitch this and then call blade angle that too, and everybody's fine. All right. Pitch. Let's go back a couple pages. Let me see. All right. Okay. Start here. 5, 6. All right. I like that. All right, so we said, and I'm just all over my notes here, but oh, this is important. Blade angle. So we'll talk about blade angle. has a big effect. I'm going to use E for E effect. Anybody wants me to use A, speak up, let me know.
Oh, God.
Blade angle has an effect. Pronounced. My notes say a pronounced effect on the amount of air moved. Air moved. And engine RPM. One degree of blade angle can change engine RPM by 60 to 90 RPMs. So if I take off my airplane, red line is 2400. I'm flying at some angle, I level off, and I pull my prop back to about 2100. I've lost how many hundreds of RPM? 300.
About 4 degrees.
That's not much, is it? I mean, when you're flying it, you're doing this. I mean, you think that this is a huge amount. It must be a lot. But if it's, that's all I'm changing it by. It's very, very little, which is really a crazy thing. Which is not to say that the blade only moves 4 degrees during flight. It moves quite a bit more. It's just between those two things. Let's see. The reason why blades have pitch distribution, twist, and many different airfoils because they move in multiple dimensions. So the reason why blades have pitch distribution twist and many different airfoils is because the blade moves in multiple dimensions. What are these multiple dimensions? And I have like 2 of them. So, what do we have? Let's talk about speed. We can do this. Same RPM, but each element has a different speed, as in like miles per hour.
Faster, farther out.
Further out you go, the faster it goes.
Yeah.
Closer you get to the hub, the lower miles per hour. And what's my limiting factor for the blade? Speed? Transonic, right? We don't want to go that fast. You can hear props that are hitting that near it. They're loud, and it's really hard on them. I've seen some videos that show how much a blade actually moves. You think they're rigid, but they're not. They're pretty fluid in flight. I had a friend who had an Ivo prop. We'll talk about the carbon fiber prop on his airplane. And when he would change, with the feet on the brakes, he would change RPMs. You would watch it just kind of do this kind of snake thing, like, whoa, I'm not standing that way anymore. Let it fly by me. All right, different rotational speeds at each element. But let's see. We'll go with this. And we have the same forward speed, hopefully. That worked out well. All right, speed. Well, I just didn't get this in there. Same forward speed. So we have different miles per hour in a circle, but the same forward speed of each element. So it's 2 completely different things that you got to match up. So what I say, see, forward moving the aircraft creates different angles of attack, same forward speed. So this creates a different angle of attack on each element. I just kind of threw that in there as my own wording. That's why the blades aren't the same. If it was the same all the way down, you would have a different angle of attack on each section. If the blade was just straight. And it wasn't twisted and it didn't look different. But they don't make it that way, so therefore they're trying to get the same angle of attack. So the twist and everything else creates, as much as possible, the same angle of attack on every single element of the blade. Let me see. So ideal, the ideal angle of attack on a blade is 2 to 4 degrees. 15 degrees is usually a stall. What's a stall? Engine just quits. Loss of lift. It's ineffective. We'll still move air. Let's see, blade angle. Blade angles are smallest at the tip and largest at the hub. That's a good place for a break.